This lecture was on collisions in two dimensions. When we talk about conservation of momentum, momentum being a vector quantity means that when we add all of the momenta to start with, it has to equal the sum of the momenta after the collision. Well, sometimes those vectors are not parallel to one another or anti-parallel, and that means we need to break them up into components. So remember that momentum is a vector and can be expressed in terms of its x and y components, as you see here. I'm just going to fix this a little bit. If you have an arrow there, it's a vector. There we go. Okay, this of course also applies to 3 dimensions. So for those of you that are going into engineering, you will be doing 3-dimensional problems. For the rest of us, we're going to stick with 2D. Okay, this means that the momentum conservation, where momentum we start with equals momentum we end with, can be solved independently for each component. And this is the same thing we did with the sum of the forces, and also what we did when we were talking about kinematics in 2D, or projectile motions. We were able to express the forces and the kinematics in x and y and treated them independently. So we're going to go ahead and do the same thing here when we talk about momentum. We're going to treat the x and y motion independently. Okay, so consider the case of a golf ball that collides elastically with a hard wall, rebounding with the same velocity, where its angle of incidence is equal to its angle of reflection, as you can see here. Is momentum conserved in this problem? The solid lines represent the momentum of the ball. Blue is prior to the collision, red is after the collision. The dashed lines are the x and y components of the momentum vectors. I'm going to go ahead and add this. So, is momentum conserved in this problem? Momentum is not conserved, and here's why. An external force from the wall is being applied to the ball in order to reverse its direction in the x-axis, in the direction of the x-axis. However, since we have an elastic collision, the ball bounces off the wall with the same speed that it struck the wall. Hence, the magnitude of the initial momentum and the final momentum is equal. So here we can see that if we take the magnitude of the final momentum, it's equal to the magnitude of the initial momentum, and therefore we have P prime equals P. So now it's time to resolve the momentum into the components along the x and y direction. Okay, so we know that the x component magnitude, let's do this, is equal to P cosine theta. Py, which is the magnitude of the y component, is equal to P sine theta. P prime x is negative P prime cosine theta. Let's make that a magnitude. And P prime y is equal to P prime sine theta. Now, we know from our diagram here that if you look at negative P prime cosine theta, which is the px prime here, then that is going to be in the opposite direction of the px here. So if we treat this as going in the x direction, this way, plus I hat, then you can see that px prime is going west instead of east, and that's where the negative comes from here. Okay? Now, if we look at py, we can see that py goes up, and py prime also goes up. So they're both going in the j hat direction. So now if we apply the impulse momentum theorem in 2 directions, we end up with the magnitude fx times delta t is equal to px prime minus px. And that's going to be minus p cosine theta minus p cosine theta, and that gives us negative 2p cosine theta. If we do the same thing using impulse and momentum in the y direction, we take the magnitude of the force Fy times the time of contact, and that's equal to, remember, delta p. So it's going to be py prime minus py, and that's going to give us 0 because we have p sine theta minus p sine theta. And so you can see that the impulse is only acting in the x direction. So, what does this tell us? So here we can see that momentum is conserved in the y direction, but it's not conserved in the x direction. The initial and final momentum in the y direction are the same. The initial and final momentum in the x direction are not the same. They're equal in magnitude, but oppositely directed. And that means that momentum is not conserved. So let's do an example. A tennis ball of mass m strikes a wall at an angle of theta relative to the normal, then bounces off with the same speed as it had initially. What was the change in momentum of the ball? Go ahead and pause the video and select your answer now, and here are your choices. Minus mv, minus 2mv, minus mv cosine theta, and minus 2mv cosine theta. Pause now. Okay, so let's look and see if you have the right answer. The correct answer is D. Remember that we have the same scenario as we had in the previous example. A tennis ball of mass m strikes a wall at an angle theta relative to the normal, then bounces off with the same speed as it initially had. What was the change in momentum of the ball in the y direction? Okay, there are your choices. Go ahead and pause the video and select your answer now. Okay, so let's see if you chose the right answer. You should have chosen B, 0. Remember, momentum is conserved in the y direction. Okay, so let's talk about general two-dimensional collisions. So now we're going to consider the more general case of two objects moving in random directions in the xy plane and then colliding. Since there is no absolute reference frame, we'll line up the x-axis with the velocity of one of the objects. Okay, this is not a head-on collision. Note how m1 heads off with a y component of velocity after it strikes m2. Also, did you see how we rotated the coordinate system so the x-axis is horizontal? So here we have m1 hitting m2, which is at rest, and then m1 goes off in a different direction. To reduce the amount of variables that must be specified, we will also use the mass of m2 at rest. The problem now is to find the momentum of n2 after the collision. This can be done by looking at the vectors first. So the momentum must be conserved in both the x and y directions, because this is elastic. Since the momentum in the y direction is 0 before the collision, it must be 0 after the collision. That's the trick. And the value that m1 has for momentum in the x direction must be shared between both objects after the collision, and not equally. It will depend on the masses and the separation angle. So if the masses were the same, that would be a different story. But if the masses are different, then the separation angles may also be different. And that means different momenta after the collision. Here's the momentum vector breakdown of mass 1 after the collision. M2 needs to have a component in the y direction to sum to 0 with m1's final y velocity, or momentum, sorry. So see this right here? This plus whatever we have for m2 must add to 0. And we need a component in the x direction to add to this piece right here for m2, so that this equals the initial momentum of m1. Okay, so remember, we start out with m1 having only x momentum. That means that the x component of the momentum of m1 and m2 after the collision has to be that value. We also know that there is no momentum for m1 in the y direction before the collision. And that means we can't have any y direction momentum after the collision. So see, this is what we have here. The momentum we start with is only going in the x direction. And that means that we can only add m1 and m2's momenta together in the x direction after the collision, and that's got to be px prime. Okay? When we add the y components, as you can see here, that's py prime. Py prime has to be 0. Okay? So this is the final momentum for m2 by vectorally adding the final px and py. So notice here, if we take this plus this is what we get. Okay, so after the collision shown below, which of the following is the most likely momentum vector for the blue ball? Okay, so there are your choices. Go ahead and pause the video now and select your answer. Okay, let's see if you selected the correct answer. The correct answer is D. And remember, that's because the y piece has to add up to 0. So this piece here has to add to a piece this way. This piece here is only about half of this line, and therefore has half this way. If you add those two together, you're going to get D as your answer. Okay, now that we've seen the vector analysis, let's run through the algebra to find the exact velocity. And we're going to be looking for magnitude and direction. That leaves m2, and we want to find that for m1 and m2 after the collision. Now, sometimes they don't give you this velocity and they just give you the masses. But in this case, they are giving us the final velocity of m2. That makes it much easier. So here we have a bowling ball that starts out with a momentum of 20.0 kilograms meters per second I hat. Let's give that a direction because it is a vector quantity. And this is also a vector quantity. Oops, I got to get rid of that because it is not in that direction. We're just going to say here that it's at 60 degrees. Okay, it strikes a stationary bowling pin, and then the bowling ball and pin take off as shown above. What is the final velocity of the pin? Okay, so before the collision, what do we have? We have that the x component is going to be 20 kilograms meters per second I hat. The y component is 0 kilograms meters per second y hat, sorry, j hat. P2 is going to be 0 kilograms meters per second I hat. And P2y is going to be 0 kilograms meters per second j hat. You may be thinking, why is she writing the unit and the unit vectors for 0? Well, here's the thing. 0 means 0, that's true. But if it's given units and a direction, then you know, 1, it's a vector quantity, and 2, that 0 represents either impulse or momentum. So it's important to me to indicate what the 0 actually is. What if that 0 were a velocity? Then it would have units of meter per second, and the direction would have to be given. Knowing what the units are for the zeros helps us to determine what that 0 actually represents. Okay, so if we look at after the collision, we end up with 12 kilogram meter per second for the momentum at a 60-degree angle. That's our direction. We're going to break that up into components, and we end up with, and I'm going to make this the magnitude. Okay, I'm not going to give these a direction just yet. So this ends up being 12 times the cosine of 60, and the units, let's do that, are kilogram meters per second. There we go. Okay, so in order to find P2 prime, what we're going to do is we're going to use Pythagorean theorem and arctangent. Okay, and this is how we find the magnitude of the final momentum, and this is how we find the angle theta. Okay, so we're going to use conservation of momentum in both the x and y direction. So in the x direction, we have p1x plus p2x, and that's equal to p1 prime plus p2 prime x. P2x prime, which is after the collision, and we're going to go ahead and solve for that. It's going to be P1x plus P2x minus P1x. We just subtracted P1x prime from both sides. Okay, so P2x prime is going to be the 20 kilograms meters per second plus 0 minus the 12 cosine of 60. Let's give it a direction. And that ends up giving us the final momentum for particle 2, M2, after the collision in the x direction as being 14.0 kilograms meters per second I hat. Okay, so now let's go ahead and look at the y direction. We take P1y plus P2y, and that has to equal to P1y prime plus P2y prime. We solve for P2y prime by subtracting the P1 prime from both sides, and that gives us 0 plus 0 minus the 12 sine 60 with the units of kilograms meters per second I hat, and that gives us a final momentum after the collision for M2 as negative 10.4 kilograms meters per second J hat. Oops, sorry, let's make this a J hat. Okay, so here are the x and y components of the momentum after the collision for M2. Okay, now that we have the x and y components of the momentum of mass 2, now we can find the total momentum. Okay, so here are the components. The x component is in the I hat direction. The y component is in the j hat direction. Now, when you take your test, you do not need to use the unit vectors. Okay, you can leave this as just plain and this with a negative, and that's perfectly fine. I don't like doing that because, to me, it leaves it like, is that really a vector? Is it not a vector? Is it a scalar? I'm not sure. But as long as you understand that this is in the x direction and this is in the y direction, and you can make that assumption because there's a subscript here, you don't have to add the unit vectors. Okay, so let's go ahead and solve for the magnitude. We substitute our numbers into the Pythagorean theorem. And notice this is wrong. Take that negative out. We're only putting in the magnitudes, okay? This is a trig function. Trig functions do not get direction. A lot of times people make this mistake of putting the negative in there, and you're not going to. Okay, now you can say, well, it gets squared. That's true, but then it also leads to this misunderstanding that we're allowed to put vector quantities into these trig functions, which only look at the sides of the triangle, the lengths, not the directions. So it's just a conceptual understanding thing there. Okay, so the magnitude is going to be 17.4 kilograms meters per second. Notice no direction, don't put it. Okay, so now let's solve for theta. Theta is equal to the arctangent of P2y prime over P2x prime. Again, get rid of the negative. It doesn't belong there. Substituting in our numbers, we end up with, I don't know what that means, 36.6 degrees. Okay, so let's see what direction that 36.6 degrees would be. Here's the x component. Here's the y component. Let me get an arrow on those. There we go. And that means that our, here we go, that the angle that we're solving for is right here. And that's going to be 36.6 degrees, and that's going to be southeast. Okay? Be careful. If you choose to put a negative in front of that 36.6, you really still have to know what quadrant you're in. I mean, what if you end up with a negative angle, but you're in the second or third or fourth quadrant? Okay, by drawing a picture or a diagram, that's what helps us to identify where we are. Okay, so this is going to be P2x prime, and this is going to be sorry, I'm writing with a mouse, it's a little bit difficult. P2y prime, and this is going to be P2 prime. Okay, instead of going through these examples, I'm going to go ahead and put them in the next video.